It's rolling. It's Monday, October 27th. So you guys should turn in your secure the fourth gravitational orbit squid. Thanks for doing that. I will get that created and put it up as soon as I can. We're starting on a new unit today. So energy, work, power, conservation energy. I guess it's going to take us probably 2 weeks exactly. And today I'm going to go through a bunch of the poster examples and I also have some video demos. I'll get you guys a quiz by the end of next week and look at. So yeah, it's just going to take us a couple of weeks. And then, okay, just for my AP classes, because my honors classes probably all going to go through the posters and video demos. But for AP, guys, I opened up over the weekend your Unit 3 energy multiple choice questions. Have those done by next Monday, so 1 week from now. I think you guys will be able to solve those definitely by the end of this week. And then I want to debrief those with you guys on Monday. That's my plan. Okay, so you guys got that? You guys know the plan? What's going on? All right. All right, so you guys ready to learn about something entirely new? All right, so guys, this being the energy, work, power, this is going to be a completely different way of thinking about things. Okay, so we've got some new variables and associated units. Okay, so capital E, just in general, called energy. You guys know here, like all the energy in this room, like power of the lights, the projection, the air conditioning, whatever breakfast you ate this morning.
Yeah.
Guys, we really need to think about this. We're starting on something totally new, right? So you really need to pay attention. Right? That energy has to come from somewhere. In fact, there's this principle in the universe called conservation of energy. You can't create energy, you cannot destroy energy. What you are allowed to do is transfer energy from one form to another form. Right? So maybe there was energy that was in a lump of coal or in a nuclear power, like from uranium, that was transferred onto the electric grid, and that's what's powering the projector right now. Something like that. Right? Guys, what do you think this J stands for? Joules. It is. It's joules. Let me show you guys here. Right, so 1 joule breaks down into 1 Newton, which is the unit of force, times 1 meter, unit of like displacement, Newton times meters, right? Which can further break down to this in terms of base SI units. So you guys know Newton is well, that'd be mass times acceleration. So kilogram meter per second squared multiplied by this meters gives you kilogram meters per second squared. Okay, so the number of kilogram meters squared per second squared that there have been in the universe for the past like 14 billion years is constant. Right? It's the same as it's ever been, same as it will be 14 billion years from now. Okay? So that doesn't change. Okay? And so now it's a lot of transfer form. Okay? And so what is work? Work is just a transfer of energy. So if you do work on an object or on a system, you can transfer energy into that system or out of that system. Okay. Right, so what are some forms that energy can take? Right, so U sub G, I'm going to call gravitational potential energy. Right, that's like energy of height or location. Right, so if you lift something, right, if I take this and I lift it, it takes some work to lift it. Right, I have to do some force times distance to lift it. And if I set this on the shelf, it does have this energy in the stored form called gravitational potential energy. All these have some formulas that go with them. I'll point them up to you guys. Okay, just show you guys the names now. You have energy in a spring. Ooh, so I got a spring scale right here within reach. So if I stretch a spring, does it take some force to stretch a spring? But also I'm stretching it some distance. In fact, the more I stretch it, the more force it takes. You guys know that from Hooke's law, don't you? And those stack of posters you got Hooke's law keyed up. Right? So there's some energy right now stored in the spring. And as soon as I let go, pow. Right, that energy, well, turns into 2 different forms. So you can store energy in the spring. Energy of motion, it's called kinetic energy. Usually I just use the single letter, but sometimes you'll see like PE or KE for things, right? So kinetic, this is energy of motion, right? So it has to have a mass and also velocity. There's a form for that. Okay? There's also a rotational form. So, oops, I got rid of my turntable. But you guys remember that turntable from last week? Okay, to give it a spin, right, there's energy associated with that. Okay, notice these are all in joules. They're all in joules because they're all different forms of energy. Okay? Now, this last green one is different. So this is power. Yeah, watts. There you go. Capital W, watts. Right, you guys ever plug in a light bulb that says like 20 watts on it, something like that? So this, guys, you can see what it is from the units. 1 watt is 1 joule per second. Hey, could that be like a rate of energy? A rate of energy? So if you have a 20 watt light bulb, could that be like 20 joules per second? It's pulling energy off the grid at 20 joules per second. And that further breaks down like this. Okay. Right, so you got to go with that. Okay. Now these last 2 lines, these blue lines we're not going to get to these for a couple of weeks. These are momentum. Okay. I just threw them on here because it's not a whole lot. Okay. All right. Any questions so far? All right. So for this class, there are these forms of mechanical energy. These are really all that you care about for the next couple of weeks. right? And really to this class. Okay. So when you do work on something, some force times distance. Right? So for example, I lift this some height, right? And I'm putting some force in it to lift it, and I'm lifting some height. That could be like a distance, force and distance. Okay. This is what's called a dot product. So you need these to be in the same direction. So force could be upward and displacement could be upward also, or something like that. Okay. Hold on to that idea. Right, I'll show you guys some power examples later. Okay. And then when I do lift it, hey, don't we have to apply a force at least equal to its own weight to lift it? That'd be called mg. And I can lift it some height, h. You see how this basically is this, just in a vertical sense? Right? So if I lift this and put it on a shelf, right, it does have some like stored energy. Okay? And then when I suppose that like I come on to the brink and it crashes off stuff, like crashes on the ground. Right. Well, now it's acquiring this energy of motion. And I'm going to skip all the way down here. You guys see it's kinetic energy, 1/2 mv squared. Right. So just memorize that for now, and I have a little bit of a derivation for you guys later. Okay. But if you take its mass, multiply by its speed squared, and then half of that, that's energy in a motion sense. Right. And if again, if you just like give us a little tap off the shelf, it came from this form of energy. So actually, this right here, going from this energy to this energy, is a really, really common setup. Going from energy of height off the shelf to energy of a crash on the floor. Right? It's just that right there. Right? You guys good so far? Now, if you think about it though, guys, this lowercase g, what is this for Earth again? And what's the number you can attach to that? 9.8 or 10 meters per second squared. But really, isn't that only true like approximately at the surface? Yeah. Like if you go halfway to the moon, I bet this number is really tiny at that point. Right. So there is actually a more universal form of this, and that's this green one right here. And I'm not going to use this very often, but this will pop up a couple of times. Okay? And this is if you have a changing gravity field. Okay, changing gravity field. For example, if you're out in the middle of deep space and you have like two asteroids that are going to collide, we'll also use this to derive escape speed, right? Because that would also involve a change in gravity field, right? So you don't see this one very often. The main ones you care about, these gold ones, well, I made them gold because I want you to mostly focus on those, right? But yeah, every once in a while you'll see these green ones pop up. There's so much news those too, okay? Right, so just know this for now, and then I'll show you guys a derivation later how this green one actually leads to this gold one. Right? So last place I got in the stack. Good for that. Spring potential energy. Now this one, I don't know if you may remember. Here, actually, we'll spoil this a little bit. Do you guys remember way back in this class, Hooke's law? Right? The force you put on a spring tells how much you can stretch it. Right? If you triple the force, it triples how much it stretches since this screws out be a straight line. You guys remember that? Right? Look, guys, look at this green triangle right here. This green triangle. Do you guys ever notice that? I label it U. Now it's for energy. It's spring potential energy. It's 1/2 kx squared. Okay. So the height of this curve goes to kx, and the base of this triangle is like x. Right. So this turns out to be 1/2 kx squared. That's the amount of energy stored in the spring. That's the amount of work that it takes to stretch this in the first place. Okay. And then if I was like, suppose it was like a spring gun, and let it go. That's how much energy it could like fire off. Okay. And remember, these are all quantified in joules, some number of joules. Right, guys, do those so far? Okay. Now look at this kinetic energy, 1/2 mv squared. Okay. Now eventually we get to rotational dynamics, which we won't do for a few months. So I'll bring out the turntables again. When you have something that's rotating, it has an inertia that's related to its mass, but we're going to call it capital I. It's also how is that mass distributed. So a few months from now. Okay? And you guys know instead of linear velocity, it has some kind of angular velocity, like it's all rotating together. Okay? So eventually, probably December, January timeframe, we'll break out this one, okay? But not for next school. Okay. All right. So let's look at some of these. So in a bit more detail, but I didn't show you guys. So I told you guys work is force times distance, right? And I specified this is what's called a dot product, so it has to be in the same direction. Right, so I'm saying, well, if I lift this some height, I have to lift against its weight. So maybe this force could be equal to its weight if I'm looking at constant velocity, right? And then some height difference. What if you're carrying up some diagonal stairs? Well, it turns out that carrying something across the room, you don't actually need to input any work. Right? Isn't true? If this was in deep space and I give it a little tap, couldn't it just like float across the room? Yeah. Right? I'm not lifting against gravity. It doesn't actually take any work at all to carry it horizontally. Right? But vertically, I do have to take some work, take some energy to lift it. So if you carry it diagonally, all that matters in terms of displacement is just the vertical direction. So wouldn't that be this f times this full distance times the cosine of this angle? You see it? So all this dot product is written with the cosine component, and the cosine is relative to the angle between them. Because what if I gave you this complementary angle? This would no longer be cosine. This would now be what? Sine, right? But oftentimes, like straight from textbook, is the angle between the two vectors, so it's defined as cosine. Right? Okay, and then what about this? What if I'm pushing a shopping cart? Now, if I'm pushing a shopping cart straight forward, it's just the pushing force times however far down the aisle I push it, force times distance, but that's all. Okay, the energy transfer. Okay, what if I'm pushing down at an angle? Down at an angle. Well, I'm not actually pushing the cart downwards. I mean, it's not moving downwards. Okay, isn't it only the forward component that matters? And that's your d cosine or your f cosine theta, and then times d. Okay, so there's still pops up a cosine theta. You guys that too? Okay. Now what about this? There's also a friction force. You guys see that from the floor? Right? Do you think that that friction force is doing negative work on the cart? Is I'm doing positive work on the cart? Yeah. So if the cart's going at constant speed, is its kinetic energy changing? No, because the speed's not changing. Huh, right? So maybe I'm putting in 100 joules to push it down the aisle, and the friction does negative 100 joules, so it's a watt. Right? So there's no net work on the cart. Okay? I'm doing positive work, the friction's doing negative work. Okay, okay. Okay. All right. If you put this on a graph, guys, on the AP exam, you're going to see this graph probably several times. Okay, right, you guys ready to look at this graph several times? A force versus displacement graph. Now here I'm showing a constant force. Maybe I'm pushing this shopping cart with a constant force. That doesn't have to be the case. Like in Hooke's law, when I bring up Hooke's law, it's definitely a variable force, isn't it? The more it stretches spring, the more force it takes. Right. So this could be any curve. This could be like some Dr. Seuss like looking curve. The area under that curve always represents the amount of work done on the system or on the object. Right? The amount of energy transferred. That's what work is. It's an energy transfer in joules. Right? Don't you get that from newtons times meters? Could represent something with the area of that rectangle there, right? Which would be joules, wouldn't it? Newtons times meters. That's joules. You guys remember that?
1J equals
Right.
1.
Yeah, yeah. There you go. Okay. Hey, you guys good with that? Okay. Again, here's the spring version of that. Okay. So this green triangle turns out to be 1 half kx squared, right? If you do the algebra on it. Okay. Because we got kx times x and then half for a triangle, so 1 half kx squared. Okay. All right. All right, let's do one that's a bit more involved here. So I've been doing these with you guys, right? Force resistance and MGH. Okay, and we did the spring potential energy 1 half kx squared, right? Now this kinetic energy one, well, here, how about this? There's something called the work energy theorem. You might see this phrase. It's that if you put work into something and you're not lifting it against a gravity field, and that energy is not going any other place, it'll go into its motion, which is called kinetic energy. Okay. So, force is equal to mass times acceleration. This acceleration starts from rest. I could sub in the kinematic form right here. It comes from the third kinematic formula. I'm just rearranging it, starting from rest. Okay. Anyway, at the end of this, you get the energy associated with motion is 1 half mv squared. Right? So m is the mass in kilograms. Speed could be the speed. Okay. Oh, and notice I'm saying speed. You know what I should have mentioned too? Here, see if you guys can figure this out. Do you guys think that energy is going to be a vector value or a scalar value? Who says scalar? Who says scalar? Yeah, right. Which means that what does not matter. The direction. Okay. So if something's moving up or to the side or at 45 degrees, that doesn't matter. You just pop in the magnitude of the speed. Okay. There's a different way you can think about this too. We haven't talked about momentum yet, but if you made momentum versus speed, you could kind of direct it that way. Okay, you guys good with the energy and motion? Kinetic energy? All right, so let's talk about systems here. So one of the first things I told you earlier today is I said that energy cannot be created or destroyed. So this amount of energy in the universe today is the same as it was like billions of years ago. Right? That's what this says right here. It says sum of energy initial equals sum of energy final. It's called anything that's a closed system. Now, you could have something called an open system where there's work being done on the system or by the system, in which case you could add or subtract some number of energy units. Right? Well, we'll see some of those examples too, but more often than not, you tend to see closed systems in this case. And then that means you can set up the conservation of energy equation, and then you can solve for things. Okay? And we'll do a bunch of examples of those. Okay, you guys get that? Okay. Here, let's take a pause here, and I'll show you guys some video demos, and we'll jump back in. All right, so let's do this one first. It's Paul Hewitt.
Let's suppose we have the case of a person up at the top of a flagpole. They're up at the top of that flagpole, and they're going to dive into a little bucket of water. They used to do this in circuses, okay? Here's a dude up here. He's going to jump. And let's suppose up at the top there, he has 10,000 units of energy. That's his potential energy, isn't it? He's at rest. So being at rest, what would his kinetic energy be? 0. Just say 0. Okay. Right into the bucket. When he gets down to the bottom of the bucket, the potential energy is what? 0. Because we took this with respect to the ground. So down here, it's got a potential energy of 0. I know you're sitting next to someone knows what the kinetic energy of splat is. I know you do the, just double check to be sure. What's the value of the kinetic energy here? How much kinetic energy? How many people don't say 10,000? Come on, you guys. It's gonna be 10,000. 10,000 units. Hey, when the dude gets halfway down, the potential energy is only.
Ooh, guys, remember potential energy was m times g times h, right? So if the height is half of the value that it was at the top, guess what his total potential energy is compared to the top? Yeah, there you go. You guys are getting this. Yeah.
Half. 5,000. There are people can calculate what the kinetic energy must be. See if
And you guys say the kinetic energy must be equal to what?
I sit next to one.
Aha. Look at it.
What's it going to be, gang? 5,000. Let's suppose when he gets 3/4 of the way down, his potential energy over here is now almost what? 1/4 of this. 1/4 of that looks like 2,500. Will the kinetic energy be more or less? You know it's going to be more. Picking up, huh? And what will the kinetic energy be at the 1/4 up amount? Huh? 75. Such that what? Do you see the rule here? Here, anywhere. Going to have the same energy. And when he finally comes down here, the kinetic energy goes to 0. Boom. Calculate the heat of the bucket and the heat of his remains. And what do you got? Then you've got 10,000 units of heat energy. And that dissipates.
All right, so we're not going to do thermal energy in this class. There's a formula that goes to that. It goes mass times specific heat capacity times the change in temperature. Yeah, so if you put a thermometer on them, the temperature would rise when it spots against the ground. But we're just going to focus on mechanical energy, which is everything on the poster I showed you guys. All right, got a couple more for you guys. For now.
Been brushing and flossing your teeth, keeping them nice and healthy, huh? Not going to do much good if this 14-pound ball come crashing through them, yeah? Watch this. I want to show you a nice physics demo. The ball doesn't smash my teeth. How come? How come? Because of a very important conservation principle called conservation of energy in physics, which states this. Take some energy to lift the ball, yeah? Now it has energy of position. Call that potential energy. I let go. It turns into energy of motion, kinetic. Back to potential, kinetic, motion, but no more potential energy afterwards than that which I start with. Try this sometime. Give the ball a little push. You better move your head. You know why? Because you gave it some energy in addition to the potential energy, and it will come higher.
Everybody knows about playing with dominoes, but what you may not know is that a domino can knock over another domino, which is about 1.5 times larger. What I have here is a chain of dominoes. Each one is 1.5 times larger than the previous one. The smallest domino is about 5 millimeters high and 1 millimeter thick. And I will carefully place it. And there are 13 dominoes. The largest domino, it weighs about 100 pounds and is more than 1 meter tall. Ready? Boom. That was 13 dominoes. If I had 29 dominoes, the last domino would be as tall as the Empire State Building. Here we go. What's the physics going on here? Well, every time you stand up a domino, you lift it against gravity, and that stores some of gravitational potential energy in the domino. And you only have to put a little bit of push to get it to that tipping point, and then you get all that energy back again when it falls over. And that's more than enough energy to knock over the next domino, which releases even more energy. So it turns out the amplification in this series of 13 dominoes is about 2 billion. So we put in a little tiny bit of energy at the beginning and we get 2 billion times as much out at the end.
Of course, none of that energy was getting created. It was being stored. Every time you had to lift one of those dominoes, so having one, they said was about 100 pounds. Ooh, yeah, you had to lift that. Right, and that gave it didn't that raise its center of mass? Right, it raised its center of mass, right? So it's like this MGH right here. The height was changed. Right? Had a bunch of M, right, and the gravity field G. Yeah, like that. Right. So let's do some of these then. All right, so. So we'll start real classic here. Galileo drops a ball from leading power. So he's gonna drop this ball. You guys, let's set up a conservation of energy. Okay, so what type of energy does it have at the very top where it's holding it at rest? Potential energy. And what's the formula for that again? MGH. Right. So here you write MGH. Right. M is the mass of the ball. G is the gravity field he's in, and height. Well, that's the height of the tower. Isn't that it? Okay. Now it's gonna fall. And right as it's about to hit the ground, maybe it's 1 millimeter above the ground, it pretty much has all what type of energy? Kinetic. And what's the formula for that again?
1/2 mc squared.
1/2 mv squared. Okay. So at the bottom, it's all 1/2 mv squared. Hey, this looks a lot like Paul Hewitt's pole jumper, doesn't it? Okay. Can you say that the MGH at the top is equal to the 1/2 mv squared at the bottom? Okay. As long as there's no air drag, energy is conserved, that would be true, wouldn't it? Okay. Now, so suppose the question was, what's the speed at the bottom, that V right there? Can you guys solve for that V? Oh, hey guys, what cancels? What cancels on both sides? The mass. And then can you cross multiply that 2? And then take, what's the last algebra step? Take the what?
Square root.
Square root. So you can solve for that V, you have to take square root. Would it be square root 2gh? Is that what that would be? Does that look familiar?
Wait,
Speed of square root 2gh?
say that.
Hang on a minute. Hang on a minute.
Say that before.
Does this look a lot like this third kinematic formula right here? Because your this from rest, this goes away. This x is like h, this a is like g. Take the square root. It's the same thing. You guys see it's the same thing? Yeah. Right. So now there's an old way of doing it, like kinematic motion, straight from your car and incline lab. Now there's a new way to think about it. Now, sometimes there's like just 2 ways to do it. So you can check your work or you have some options how to solve it. Sometimes there's a better way to solve it. Like, okay, well, actually, it's better if you stick to kinematic, or sometimes it's actually a lot simpler to stick to this new energy method, depending on some types of questions. Okay, so yeah, so let's draw that too. I should point out too, guys, what variable from kinematic days have you not even seen today, other than on this poster right here? T, time. You guys see that? You guys notice that? Yeah. So, well, depending on how you look, yes. So usually you're not going to see questions involving time. I mean, there might be a couple of examples, like power could be a rate of energy, but typically, yeah, you don't. Time is not going to show up in your conservation of energy equations. Okay, so we don't know how much time it took necessarily to reach the bottom. We just know the speed at the bottom is very huge. All right, let's do another one here. Ooh. So you throw a ball straight upwards. Throw a ball straight upwards. Okay. Now this one I got two ways of doing it. Got a kinematic way and I got a conservation of energy way. Okay. So here's the old kinematic approach. Hey, look, that's that third kinematic expression. The one that doesn't have the time in it. Okay. And the new way is conservation of energy. Now you can either, if you know how fast you can throw this V naught, you can solve for H max, how high does the ball go, or vice versa. Suppose you and some friends get together and you start throwing some balls against the edge of the skyscraper. I can throw up to the 5th floor, right? You see how high you can throw. I bet you can back calculate how fast you can throw it. Can you do that either way? Okay. And the old way to do it was with kinematic approach. So it goes like this. So there's the maximum throwing height, based on throwing speed. Or if you rearrange it, here's how fast you can throw based on how high it goes. Kind of like a square root 2gh again. You just saw that, right? Or with the energy method, guys, at the bottom, it's what kind of energy? Kinetic energy, 1/2 mv squared. And at the top, it's all what type of energy? Potential energy, MGH. So couldn't you just set those to each other like that? Like that? Okay. And then again, you could solve for V naught or H, depending on which what numbers you have. Okay. There's H is that, there's throwing speed is that. Hey look, it's the same thing. It's the same thing. You see? Exact same thing? Okay. Just a totally different way of thinking about it. But it gets you to the exact same answer. Yeah. All right, guys got that? All right. How about a car coasts uphill? Well, yeah, let's do uphill. Ooh, you guys know that diverging diamond that goes over I-95? Right. Suppose you're driving at some speed, right? You take your foot off the gas pedal, you let your car just coast up that hill. Right? You still got some speed at the top of the hill, right? Okay, you're still in motion. Right? So you got some speed. But guys, are you moving faster or slower at the top? So your car's been slowing down the whole time. Right? And we're ignoring frictional losses, but still your car slows down anyway just because it has to climb this height. Right? So what type of energy does your car have at the bottom of the valley here? It's all kinetic, isn't it? Right? And at the top, do you still have a little bit of kinetic?
Yes.
Yeah, because the car's in motion, but you also have a lot of what? Potential energy. Right? So now, again, ignoring frictional losses, you can set up a conservation of energy equation to solve this. Right? So what expression do you write on the left side?
One half is squared v squared.
Yeah, 1/2 mv squared, where the v refers to this bottom v right here. The bottom. Right? And on the right side, ooh, I bet you have a mix of energy. You have what plus also what?
MGH plus 1/2.
Yeah, mgh plus 1/2 mv squared. In this case, it's a different speed. Of course, it's the top speed. Right? Right? You guys can come with the first one. Okay. Now, of course, if I gave you some speeds and I gave you the height of the hill, but you could solve for anything you didn't have. If I gave you the bottom speed and the height of the hill, the gravity field, you could solve for how fast the car goes to the top. You did that, right? Oh, guys, does the mass of the car cancel out right here? Yeah. But whenever you're dealing with just kinetic and gravitational potential, the mass always ends up canceling out. So whether I tell you the mass of the car or not doesn't matter. Or if you had like a little tiny motorcycle next to a big old semi truck, they should have, they start out side by side, and they both coast up the hill. They both have the same speed at the top. Yeah, that's what that says too. Okay. Ooh, this next one's fun. Okay. All right, so I got a block spring earth system. So I'm gonna push this block against the spring. So I just squashed the spring by some amount X. It took some force to do that, didn't it? It took some force times some distance. I think I did some work compressing that spring. Then I'll let it go. It's gonna fly around this loop right here. Okay. So what kind of energy did it have right here when it was compressed? When the spring was compressed? Spring potential energy. You guys, what's the formula for spring potential energy? 1/2 kx squared. Yeah. But guys, by the time we get to this part of the year, students commonly mix up two different formulas for springs. There's 1/2 kx squared is the energy stored in the spring. F equals kx. Kx, that's a force. Guys, is a force an energy? No, those are different things. Force is how much are you pushing on something. Energy is like how many. Well, that's a different concept. Right? It's like conservation of energy measured in joules. Right? Yeah. So I'm going to set a conservation of energy equation here. Maybe my question could be like, how fast is it moving at the top? Okay, maybe that's my question. How much is the speed up here? So I got my 1/2 kx squared. That's like the source of all the energy. True? Is that okay? Okay. Then I let go. Go fly around. What type or types of energy do you think it has right here? Yeah, gravitational potential and also kinetic. Right? It better have some speed. Because if it has no speed, is it just going to just fall off the track? Yeah, so it better have some speed. I bet it better have some minimum speed of, what was that from last week? Was it square root GR? I think so it was. You fit some circle up here, square root GR. It better be that you at least have speed or faster. So what does the rest of this formula look like?
MGH 1/2 mv squared.
Aha, you guys got it. Yeah. MGH because that's climb this height. Plus 1/2 mv squared has something to do with its motion, right? And notice these are all, of course, energy terms. So if I have 100 joules here and like 30 joules here, I bet I have 70 joules to go here, right? Because 30 plus 70 adds up to the original 100. Can you do that? Right. Okay, let's take a break right here and solve one of these. Okay, let's solve this one right here. So what if I give you, say, mass equals 10 grams. I'll give you guys a gravity field of 10 meters per second squared. I'll give you guys, how about, I need to give you a K and an X and an H. Okay. So let's give a spring constant of like 500 Newton per meter. I'll say I squash this by, how about 15 centimeters? Let's say this height right here is like 40 centimeters. Okay. Okay. Now I just made up those numbers from scratch right now, so I hope it's going to make it around, but we're going to see. And if it does make it around, how fast is it going? You guys get that? Okay. So we got these numbers right here. And here, I'll go ahead and copy this down because you guys got this part already. So, okay. Well, I know that sum of energy initial equals sum of energy final. Okay, that's what we're saying. Okay, okay, for that case. Okay, maybe we draw that picture. So we're doing like going like here. So we got the spring, we got this mass. Yeah. That's the question. Is what is the speed? Yeah, you're trying to solve for the speed right here. That's the question. Okay. There's this height change. Okay, so you guys got the spring has some constant K in it. Okay. Got that set up? Okay. Okay. And you guys told me that all the energy was in the spring, so that's 1/2 kx squared. And by the time it gets to the top, well, it would have an energy that it has to climb to that height, so something with NVH. Whatever's left over goes into its motion, 1/2 of v squared. Okay. And our goal is solve for this v. How fast is it going to the top? You guys got that? Okay, the numbers I gave you, can you feed those numbers exactly into this equation? The same numbers? Like, can I put this in this 15 for this x right here? No, why not? Yeah, they need to be in base SI units. So let's go from the top. 10 grams. The number that goes in the calculator is actually what? 0. What? 0.10 kilograms. Yeah. Okay. No, gravity field looks okay. Okay. Spring constant looks okay. Ooh, what about how much I smashed the spring? 0.15 meters. And then the height of this climbs 0.40 meters. Okay. All right. All right. So let's put these numbers in. So you got 1/2. The K is 500. That's feet per meter. This X is 0.15. That's meters. And that's being squared. Okay. Then, guys, does the mass actually cancel out on this one? Yes or no? It does not. Yeah. Normally, when a spring is involved, then the mass does not cancel out because the mass is not part of that expression. So you have to plug in mass. 0.010 kilograms. Yeah, 10 meters per second squared. And height of 0.4 meters that climbs up to. Okay. Then plus 1/2 is 0.10 kilograms times speed we're solving for squared. Be like that. All right. Calculator time. Okay. How much energy are we even talking about? What's 1/2 times 500 times 0.15 squared? That looks like 5.6 joules. 5.625 joules. Okay. So that's all the energy that's ever in the system. It's like 5.6 joules. That's all I have to work with. Oh, did I say frictionless here? Yeah, no friction, right? No friction. Okay, so that's why I didn't subtract out any friction. Okay, so where's that energy go? 0.01 times 10 times 0.4. Okay. Oh, wow. Okay, so very, very little of it actually goes into lifting at that height. And so that's like, yeah, 0.04 joules goes into like lifting it against gravity. Okay. Okay, so I didn't have to. I was what I was worried about was what if I make this mass too heavy? Guys, if mass is too heavy, do you think it doesn't even make it to the top at all? Yeah. Okay, so that's why I made it kind of a tiny mass, but yeah, I got plenty of spare energy left over for motion. Right, so no worries at all. So this is well, I don't know what this number is, but how many joule? We could find that. It's so many kilograms times v squared. Okay. Thanks, let's take that. Okay. Okay, so then let's see, subtract this over. What's 5.625 minus 0.04, and then divide by 0.005, and then take the square root. Okay. Okay, you guys got that so far? Okay, so what I'm getting at the end is V equals 33.4 meters per second. All right, you guys get the same thing back? Oh, like that. Now, let's see. Next class, like you guys, if I like have 10 times the mass, that would still plenty work out. Like, no issue. All right, guys good? Block Springer system. You guys do block Springer? All right, what I got next here? Oh, it's this one, bungee jumper. So actually, I pulled this one pretty much straight off an AP pre-response question from the past, modified a little bit. But suppose this guy's at the top of this cliff right here. And he's going to jump. It's attached to a bungee cord, and the unstretched length I'll call L naught right here, unstretched. Right? And then suppose the stretch is some additional amount S, and that's like the maximal stretch. Right? And then after that, you're supposed to just reach down like point, just touch the sidewalk, and then retract and boing. Right? So it's just barely long enough to okay. So what guys? What kind of energy at the very top here? Yeah, it's all in. Oh, and what's the expression for that? What's the expression? MGH. MGH. Isn't it all? If I said the conservation of energy expression, shouldn't it be all MGH at the top? Right. Because this H, what is this H in terms of L and X? Yeah, it's L plus X, isn't it? Like that. Okay. Right, so that's the energy at the top. Like if you're told the unstretched length and then the maximum stretch amount X, you could say, oh, well, that would have to be the height in this case. Right? Okay. Now, by the time it gets to this point right here, where did all the energy go into?
Right.
Yeah, the spring, the bungee cord, which I'm treating as a spring. Yeah. What's the formula for that?
Oh, 1/2 kx squared.
1/2 kx squared, exactly. Okay. So what have we got? I got 1, 2, 3, 4, 5 different variables going on. If you had 4 of those, could you solve for the 5th one?
Yeah.
Yeah, you do that, right? Right, that's it. All right. Next one. Here, I'll go ahead and show you this whole thing. All right, so this one's been involved. I really like this question, but it does take a few minutes to set up and solve. The premise is this: if you're released from the top of the hill on a roller coaster, there's no frictional losses. Don't worry about that. Okay? And you go around a vertical loop. Right? And the roller coaster's not being powered along the way. It's just, well, it was powered to be lifted in the first place. But after that, just coast around. Now, do you guys think there's some minimum hill height to guarantee that you safely make it around this loop? Do you guys think? Okay. Like, what if the hill was this tall? Would you ever make it around this loop? Definitely not. Yeah, you know, best you can make it up to about here, and just fall back or something like that. Okay. What if the hill was the same height as the loop? Would you make it around?
No.
You would not, because you guys remember from last week or last couple weeks. Remember there is a minimum speed to get around the top of the loop. Remember it's square root GR based on this R here, square root GR. It's actually be going at least that fast. So I bet the hill has to actually be taller than the slope. Isn't that true? Right. We have a video for this too. Let's check this out. All right, so we got the bowling ball at the top of the loop. Now, part of the bowling ball top of the track. Now, part of this does involve the bowling ball is going to rotate. We're not going to worry about that until well, for a few months. But for now, we'll treat that as a point mass. We'll ignore the rotation of the bowling ball. And this guy, whoa, okay, yeah, he's okay. Wear the helmet, probably a good call. But...
Catch the portal. Hold on.
Yeah. Oh yeah, just catch a bowling ball. So I wonder
That's good.
if this is like point B, right about here. Well, somewhere right here, right? So pretty much top of that loop. Right. It does have to have some minimum speed to get around. That had something to do with the original height of the hill. Right? You guys get that premise? So maybe that's the question: is what is the necessary minimum height of the hill? And it turns out it's strictly a function of this radius. And the gravity field and the mass of the cart end up canceling out this process. So there's a 2-part process. You go back to last week. You say, well, at the top, you can set up this expression right here. And if it just barely gets around, wouldn't the normal force from the track pushing it down go to 0? Right. And what you're left over with is, well, the minimum speed is square root GR, just like it was. Right. You guys remember I had that cup of water that's flying around a vertical circle? Right now, we're going to hold on to that. Then we're going to go over to conservation of energy. We're going to say, guys, what kind of energy at the top of the hill here? Yeah, potential energy, MGH. Now, if this is the H that we're measuring with respect to it, that means we're defining the floor down here. Actually, that's something you have to do too. I meant to specify that earlier too. You have to define where the floor is. So I'm going to define the floor all the way down here. This is my H. And if that's true, by the time you get to this point B in question, it does have some height. Because what is this height right here? 2R. Yeah, you see that? 2R? Right? So by the time you get to the final point, it does have some potential energy, mg2r. And it better also have some speed, hence some kinetic energy, 1/2 mv squared. In fact, that v squared has to be at least as big as this v squared. Now, it could be bigger, it just can't be less. And we're solving for minimum height of the hill. So I'm going to plug in this for this v squared. You see that? Okay. You do a bunch of algebra. And this, it always ends up being, this is a really classic physics question. And the answer to this, if you guys take physics in college, like almost for sure you're going to see this question, and the answer is always this. It's always 2.5 times the radius. Okay, so you take here's one radius, here's two radius, and then take a half and add it to that. So like right here, bing. If you release this cart from here, you might just barely get around. And of course, anything about that, it's okay. Okay, guys, good. Right.
Is it solving for minimum height?
Did I ask? I forget if I asked this before.
That makes
You
sense.
guys see how this vertical loop is a circle? Right. But in real life, they don't look like circles. Don't they look more like teardrop shape? Like teardrop shape. Did I ever ask you guys why teardrop shape? Why not actual circles in real life?
I don't need to notice when I'm
Okay. Like think about from the experience of riding along. Okay. Guys, if so draw two tracks here. What if you like went into like an actual circle loop versus in real life these more look like teardrop shapes, don't they? Something like that. Okay. Why is this a better design than this? Okay. So guys, if you're riding along in your cart,
only a fictional person.
right in a cart, okay, and then you suddenly hit the circle, you go from a straight track to a circle, then doesn't that well, I'll call it centrifugal force just like hit you all of a sudden? And it'd be really jarring, wouldn't it? Yeah, it'd be really jarring. Okay. Versus here, you guys see like here, yeah, like a really large radius circle, and here's kind of a medium radius circle here, and then here's like a small radius circle that's flush to the curve here. Okay, so it's more like a gradual buildup. So the centrifugal force kind of gradually increases. Okay, so it's less jarring. Okay, so that's a little bit safer direct. For sure. Okay. Now back in the 1920s, roller coaster loops look more like this, but people found out the hard way. Okay. I guess it. This next one. Hey, this looks like Paul Hewitt's bowling ball. Paul Hewitt's bowling ball. Okay. So what we're gonna do is take a mass, okay, lift it some height. Now it turns into a pendulum. We're gonna let this go. Okay. And I wonder what is the maximum speed of the pendulum at the bottom. You guys get that? This is a lab I'm planning for you guys too. You guys remember the speed gates? I'll have you guys actually construct these and then put the speed gate upside down here and let mouse goes through the speed gate. How do you do this calculation and compare to the number on speed gate? And in the past, this has worked out really well. Okay. So take a conservation of energy type equation here. Right, guys, ready for this one? This one's a little more involved because there's some geometry involved. Guys, when you're holding this at right here, what type of energy? Yeah, there you go. Potential energy MGH. Now, if you gave it a push, would you also have to add a 1/2 mv squared to it? Yeah, you could do that. Now, here I put it in gray because that's not asked very often, but it could be asked, so you want to consider that too. Okay, but usually, you just okay. Then, you guys, when it gets to the bottom, if you define the bottom as like the zero height condition, zero height right here, that means it has all what type of energy at the bottom? Kinetic. There's your 1/2 mv squared. So doesn't that turn into that basically? Is that okay? Now, where the geometry kicks in is what is this height change as a function of this length and this angle? Because guys, if I only pull this back like 2 degrees, there's almost no height change at all. If I pull this back 90 degrees, because if this theta goes all the way to 90 degrees, isn't this height equal to the length of the string itself? Yeah. What if I pull this back to like 38 degrees or something crazy? What is this height? Can you guys figure this out by geometry? Here, I'll walk you guys through it. You guys see a nice right triangle right here? Is this leg of this triangle L cosine theta? Right, here's L. Exactly. Yeah. You guys see that? Here's the full length of the string L. This is L cosine theta. The height change is just L minus L cosine theta. Isn't that exactly what H is? You guys see that? All right, I'll show you the rest of it. Okay. So H is L minus L cosine theta. Oftentimes you'll see the L factored out. You don't have to, but you could. Leave you with L times 1 minus cosine theta. So if you see that, you know where it's coming from, right? Okay. Right. Then you can substitute that into this height right here. Okay.
I didn't see that.
Actually, I did skip a few algebra stuff, so I'll write you guys some algebra steps and some notes right here. Okay. So we got conservation of energy, sum of energy at the top equals sum of energy at the bottom. I got some MGH at the top. Here, I'm going to throw in this 1/2 mv squared because I want you to see how that would play out if you gave it a push. So I'll throw that in too. And at the bottom, it's all 1/2 mv final squared, which of course is a different speed. And I'm solving for what is that v final. Okay. Guys, does the mass cancel out? Yeah, because they have 3 terms. They all have the mass. So it doesn't matter what the mass is. The answer is the same regardless. With the speed at the bottom. Right. Guys, I'm going to substitute for this h. I'm going to substitute this expression right here. L1 minus cosine theta. So L 1 minus cosine theta. Okay. And then plus 1/2 V naught squared equals 1/2 the final I'm solving for it. That here. Gonna multiply everything by 2.
Oh, yeah.
So 2GL 1 minus cosine theta
I swear.
plus V naught squared equals V naught squared. Okay. You guys, what's the last algebra step to do what both sides? Square root. Yeah, you guys see square root? Okay. And that leads exactly to this. Okay. Now, guys, here's a really common misconception. Okay, guys, should I say V final equals V initial plus the square root of blah 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 blah, or that's option A, or option B is V final equal to the square root of V initial squared plus blah 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 blah. Guys, which one of those is correct? A or B? B. Who says B? Who says B is correct? Yeah, that's right. Right here. Guys, that's a really common mistake that students will make too. You can see right here, because I wanted you guys to see what happens if you give it a push. That push shows up as V squared inside the square root, and then you do plus. All right. So I think we made pretty good progress today. So when you guys walked in class, I did give you guys this packet. We'll be working on this packet too throughout the week. Okay, but yeah, we are about out of time today.